Good morning students. Last class we discussed about some problems related to GCD and LCM. In the previous classes already we discussed natural numbers, whole numbers, integers and so on. Okay. So in this class we are going to discuss next number system, that is rational numbers. Rational numbers means they are in the form of P by Q. A number is said to be a rational number. It must be in the form of P by Q. Here P and Q are integers and Q is not equal to 0. A number is said to be a rational number. It must be in the form of P by Q. P and Q are integers. Denominator must be not equal to 0. This number system is denoted by Q. The numbers are denoted by in general X such that it must be in the form of P by Q. P and Q are integers and Q is not equal to 0. For example, examples 2 by 3, 4 by 7, minus 2 by 7, 7 by 14, etc. are the examples for rational numbers. Okay. Here observe, suppose rational number, so it is in the form of P by Q. Suppose GCD of P and Q. GCD for P and Q is equal to 1. So GCD means greatest common divisor. Greatest common divisor is 1, means P and Q have no other common divisors other than 1. The greatest common divisor is 1. Suppose if P and Q have greatest common divisor is 1, then we call P by Q is in the lowest form. The lowest form. For example, here observe GCD for 2 and 3 is equal to 1. GCD for 4 and 7 is also 1. GCD for minus 2, 7 is also 1. But here observe GCD for 7 and 14 is 7 It is both are divisible by 7. Greatest common divisor is 7. So therefore it is not equal to 1. Therefore 7 by 14 is not in the lowest form. Lowest form of 7 by 14 is simplified. It is divisible by 7. 7 1 ja, 7 2 ja. So lowest form of 7 by 14 is 1 by 2. Okay. We can also represent all the rational numbers in the decimal form. In the decimal form we have two types. One is terminating decimal expansion, another one is non-terminating decimal expansion. Before going to know about terminating or non-terminating decimal expansion, first consider some rational numbers and then represent in the decimal form. Okay. First, consider rational number 1 by 4, 3 by 4, 8 by 120, 8 by 120, 1 by 3, 1 by 7, 5 by 11, here. 7 by 44, 3 by 22, 17 by 44. These are the rational numbers. First represent in the decimal form 1 by 4. So 1 by 4 is 0.4. 0.25. 1 by 4 is 0.25. 3 by 4. 3 by 4 is 0.75. 0.75. 8 divided by 125. 8 divided by 125 is 0.064. Next, 1 by 3. 1 by 3 means 0.33333 repeated. This can be represented as 0 point. Here the digit 3 is repeated, denoted by 3 bar. It says that 3 is repeated, 333. Okay. Next, 1 by 7. 1 by 7 is 0.142857, 142857, etc. Okay. Next, 5 by 11. So this represented as, here observe, 142857, 142857, 6 digits repeated, 6 digits are repeated. This can be represented as 142857 bar. Okay, 6 digits repeated. Next, 5 by 11. 5 by 11 is 0.4545, etc. Here 2 digits are repeated. This is denoted by 0.45 bar. 0.45 bar means 45 is repeated. 0.454545. Okay. Next, 7 by 44. 7 by 44 is 0.15909090. So 90 is repeated, is denoted by 90 bar. So next, 3 by 22. 3 by 22 is 0.13636363 to etc. It is denoted by 0.13. Here observe, 63 is repeated. So 63 bar. Here also this is 0.15909090, etc. Okay. So here 17 by 44. 17 by 44 is 0.386363, etc. Therefore, this is denoted by 0.3863 bar. 63 is repeated, so 63 bar. Okay. Here observe. Here, after decimal point, all the digits are not repeated and ended after certain stage, means terminates. So this type of decimal expansion is called terminating decimal expansion. This is called terminating decimal. Terminating decimal expansion. The word terminate, it itself says that terminate means end, means after decimal point all the digits are not repeated, and as well as end after certain stage. It has end at certain stage. So this type of decimal expansion is called terminating decimal expansion. Here observe, after decimal point all the digits are repeated. 3 is repeated here after certain stage. All the digits are repeated after certain stage. Here 1, 4, 2, 8, 5, 7. 6 digits are repeated after certain stage. So this type of decimal expansion is called recurring decimal expansion. Recurring decimal expansion. Here the word recurring means, it says that recurring means reoccur or repeat. The word itself says that digits are repeated. Recurring means repeated. After decimal points, digits are repeated. But here observe, after decimal point, in the decimal expansion, after decimal point, some 1 5 is not repeated. So some digits are not repeated and some digits are repeated. Here observe, 1 3 is not repeated, but 6 3 is repeated. Here 3 8 is not repeated, 6 3 is repeated. Means in the decimal expansion, after decimal point some digits are repeated, some digits are not repeated. So this type of decimal expansion is called mixed recurring decimal expansion. Mixed recurring decimal expansion. Okay. Okay. We have a formula to easily verify given rational number having terminating decimal expansion or non-terminating or recurring decimal expansion, that is so consider rational numbers. It is in the form of P by Q. Suppose consider denominator. So prime factorization of Q. Prime factorization are also called canonical representation or canonical form. Canonical representation of Q is of the form 2 to the power of n into 5 to the power of m. 2 to the power of n into 5 to the power of m. Canonical form of denominator Q is 2 to the power of n into 5 to the power of m. Then given rational numbers having terminating decimal expansion, otherwise having non-terminating decimal expansion. So in the exam, and the question will be asked like this: without actually performing the long division, verify whether given rational numbers are will be having terminating decimal expansion or having non-terminating decimal expansion. Okay. Now let us discuss some problems. Okay. Here question will be like this: without actually performing the long division, state whether the following rational numbers will have a terminating decimal expansion or non-terminating decimal expansion. First problem: 17 by 3125. Okay. So without performing long division. Okay. So to check this rational number having terminating decimal expansion or non-terminating decimal expansion, first represent denominator in the canonical form. Okay. Therefore consider denominator is 3125. So in the unit place we have 5. So therefore this whole number is divisible by 5. 5 6 are 31. So 5 2s are 10. 5 5s are so 625. Next it is divisible by 5. 5 1s are, next 5 2s are 10. 5 5s are 25. Again it is divisible by 5. 5 2s are 10. 25 5 5s are 5 5s are. So 5 is a prime number. Therefore 3125 can be written as 5. 1 2 3 4 5 times. So 5 to the power of 5. But we want denominator to prove the given rational number having terminating decimal expansion. We want to prove decimal form in we want to prove denominator in the form of 2 to the power of n into 5 to the power of m. N and m are any positive integer. 5 is there, 5 to the power of m means here 5, but we want 2 to the power of n. Okay. Here observe, this can be written as 5 to the power of 5 into 1. 5 to the power of 5 into 1 is 5 to the power of 5. So 5 to the power of 5 into here 1 can, we want 2 to the power of n. So 1 can be written as 2 to the power of 0. So 2 to the power of 0 is equal to 1. 3 to the power of 0 is equal to 1. 4 to the power of 0 is also equal to 1. 5 to the power of 0 is also equal to 1. So anything with power 0 is equal to 1. Therefore 1 can be written as 2 to the power of 0. We can write 1 in place of 1, 2 to the power of 0. So it is in the form of 2 to the power of m into 5 to the power 2 to the power of n into 5 to the power of m. 2 to the power of n means 0, 5 to the power of m. m is 5. Therefore, given rational number means 17 by 3125 has terminating decimal expansion. Given rational number has terminating decimal expansion. Okay. Next problem. Second problem, 13 by 8. Yes, verify. Given rational number having terminating decimal expansion or non-terminating decimal expansion. Here observe denominator. Denominator is 8. What is the canonical form for 8? Canonical form for 8 is 2 cube. We know that canonical form for 8 is 2 cube. Okay. Prime factorization or canonical form for 8. Prime factorization of 8 is equal to 2 cube. We want denominator must be in the form of 2 to the power of n into 5 to the power of m. Okay. So this can be done as 2 to the power of 3 into 1 can be written as 5 to the power of 0. 5 to the power of 0 is equal to 1. So therefore this is in the form of 2 to the power of m, 2 to the power of n into 5 to the power of m. Here m value 0. Therefore given rational number 13 by 8 as terminating decimal expansion. Terminating decimal expansion. Terminating decimal expansion. Okay. Next problem. Next, third one, 31 divided by 243. Okay. So here also to verify given rational number having terminating decimal expansion or non-terminating decimal expansion, verify denominator. It is canonical form of the denominator. It is in the form of 2 to the power of n into 5 to the power of m or not. So consider denominator. Denominator is 243. So it is not a even number, so it is not divisible by 2. Here sum of the digits 2 plus 4 6 6 plus 3 9. 9 is divisible by 3. Therefore whole number is also divisible by 3. 3 8s are 3 1s are 3 81 are 243. Again it is divisible by 3. 3 2s are 6 21 3 7s are 3 9s are 27 3 3s are. Therefore 243 can be written as 3 1 2 3 4 5 times. So 3 to the power of 5. Here observe 3 to the power of 5. Suppose, but we want denominator must be in the form of 2 to the power of n into 5 to the power of m. Suppose if we write 3 to the power of 5 into 1 into 1, no problem. 3 to the power of 5 into 1 into 1 is 3 to the power of 5. 3 to the power of 5 into 1 can be written as 2 to the power of 0. 2 to the power of 0 is 1 into 1 can be written as 5 to the power of 0. 5 to the power of 0 is also equal to 1. But suppose if we write 2 to the power of 0 into 5 to the power of 0, but here observe it is not in the form of we want only 2 to the power of n into 5 to the power of n, but here we have extra one term 3 to the power of 5. Therefore, it is not in the form of 2 to the power of n into 5 to the power of m. Therefore, given rational number having non-terminating decimal expansion, it is not in the form of 2 to the power of n into 5 to the power of m, 2 to the power of n into 5 to the power of m. Therefore, 31 divided by 243 as non-terminating decimal expansion. Non-terminating decimal expansion. Non-terminating decimal expansion. Okay. Next, we have 2 more problems. Fourth one, 139 divided by 2 to the power of 3 into 5 square. Here observe, denominator already in the canonical form. So, denominator 2 to the power of 3 into 5 square. Denominator is here 2 to the power of 3 into 5 square. It is in the form of, already it is in the form of 2 to the power of n into 5 to the power of m. Here n value 3, m value 2. Therefore, given rational number 139 divided by 2 cube into 5 square as terminating decimal expansion. Terminating decimal expansion. Terminating decimal expansion. Okay. So, next, last problem. Last one, 129 divided by 7 square. Okay, verify. Given rational number having decimal expansion or non-terminating decimal expansion. Verify. Given rational number having terminating decimal expansion or non-terminating decimal expansion. Here observe denominator. Denominator 7 square. It is not in the form of not in the form of 2 to the power of n into 5 to the power of m. Denominator 7 square. It is not in the form of 2 to the power of n into 5 to the power of m. Therefore, given rational number 129 divided by 7 square as non-terminating decimal expansion. Have as non-terminating decimal expansion. Okay. Okay. In this class, we learnt about rational numbers, terminating decimal expansion, non-terminating decimal expansion or recurring decimal expansion and also mixed recurring decimal expansion and some problems. Okay. In the next class, we will going to discuss next number system, that is irrational numbers. Thank you.